Namaste, this is Moulya, studying in Sri Venkateshwara College of Engineering from CSE AI department, and today I am gonna present about quicksort and its time complexity under the subject Design and Analysis of Algorithms. The topics to be discussed are Introduction to quicksort, how quicksort works, quicksort algorithm, time complexity analysis of quicksort, how to solve a problem using quicksort, and finally conclusion. Before moving to the quicksort, let us know what sorting means. Sorting is the process of arranging data into meaningful order so that you can analyze it more effectively. Data sorting is any process that involves arranging the data in some meaningful order to make it easier to understand, analyze, and visualize. Data is typically sorted based on actual values, counts, or percentages in either ascending or descending order. Let us know the types of sorting: insertion sort, selection sort, bubble sort, quicksort, heap sort, and merge sort. And in this presentation, we are gonna discuss about quicksort and how it works. What is quicksort? Quicksort is a highly efficient sorting technique that divides a large data array into smaller array. A vast array, it is divided into two arrays, one containing value smaller than the provided value, says pivot value, on which the partition is based. The other contains value greater than the pivot value. This sorting algorithm uses the idea of divide and conquer. How quicksort works? As we have discussed in the previous slide, quicksort divides a vast array into two sub-arrays. So it works by breaking an array into smaller ones and swapping the smaller ones depending on a comparison with the pivot element picked. So there are certain steps to be followed in quicksort. They are pick, divide, repeat, and combine. This means select an element, split the problem set, move smaller part to the left of the pivot and the larger items to the right side, and repeat the steps and combine the arrays that has previously been sorted. So here is the quicksort algorithm. So algorithm quicksort of array, low, high. We are using a if condition. Low is less than high, then pivot is equal to partition of array, low, high. We have to do the quicksort for array, low, pivot minus 1, and again the quicksort for array, pivot plus 1, high. So here we can see the algorithm partition. Int partition of array low, int low, and int high. So int pivot value is equal to array low, that is int I is equal to low plus 1 and int j is equal to high. So while low is less than high and while I is less than high, ampersand a of I is less than or equal to the pivot value. Here I is equal to I plus 1, while j is greater than pivot value, j minus minus. We are using a if condition. I is less than j, then we have to swap a of I and a of j, else we have to swap a of j and the pivot value and return j. Now we are going to discuss about time complexity analysis of quicksort. In this we are going to discuss about best case efficiency, average case efficiency, and worst case efficiency of quicksort. First, we are going to discuss about best case efficiency. Quicksort best case time complexity is omega n into log n. Quicksort's best case occurs when the partitions are as evenly balanced as possible. That is, their size either are equal or within one of each other. Next comes the average case efficiency. Quicksort average case time complexity is theta n into log n. The average case complexity occurs when the array elements are in the jumbled order, which means it is not arranged either in a ascending order or not properly in a descending order. Now at last comes the worst case efficiency. Quicksort worst case complexity of O n into 2. The worst case occurs when the given output array is sorted reversely and we choose the rightmost element as the pivot element. Now let's solve a problem using quicksort. Taking an example, So here are the list of elements 3, 2, 5, 0, 1, 8, 7, 6, 9, 4, and here are the index number of these elements. 4 is considered as the pivot element. So here are some conditions we have to use for quicksort. If number is greater than the pivot value, then we have to pass the given element. If number is less than or equal to pivot value, then we have to use the conditions, that is index element plus 1. These are the index numbers of these elements. So now if number is greater than pivot element, then we have to swap the element, and if number is equal to pivot element, then we have to pass the. As we go on comparing the given elements with the pivot element by applying the conditions as discussed in the previous slide, we can observe that 0 and 5 has been swapped because 3 is less than the pivot value, that is 4, and 2 is also less than the pivot value, that is 4, but 5 is greater than the pivot value. So as per the condition, 0 and 5 have been swapped. Again 1 and 5 get swapped as 1 is less than 4 and the index value plus 1 is also greater than 4 as shown in the table below. Now here you can observe that 1 and 5 have been. Now as elements 8, 7, 6, 9 is greater than 4, and according to the condition the elements won't get swapped. Now as 4 is equal to 4, according to the condition 4 and 5 should get swapped with, as index element plus 1 is also greater than 4. Here you can observe in the table that 4 and 5 have been swapped. So 4 is the pivot value and the elements to the left side are smaller than 4, and the elements to the right side of the pivot value is greater than 4. Now recursively we have to sort each half of the list, that is 3, 2, 0, 1, and another half is 8, 7, 6, 9, 5. Now you can observe the original list of elements, and this is the list of elements got swapped. So here again considering the condition, at first 0 and 3 got swapped because 3 is greater than the pivot value 1, 2 is greater than the pivot value 1, but 0 is less than the pivot value 1 and the index value is plus 1. So 0 and 3 get exchanged, and again 2 and 1 got swapped as shown in the table below. Now coming to the second half of the elements, 8, 7, 6, 9, 5 is the original list of elements, and this is the list of elements that have been swapped. So considering the second half, the element 8, 7, 6, 9 is greater than 5. So the elements won't get swapped, but 5 is equal to 5. So 5 get swapped with 8 because index value plus 1. So 5, 7, 6, 9, 8 is the sorted element of list. Now let's continue the sorting process of 3, 2, 0, 1, 4, 8, 7, 6, 9, 5. Here 4 is the pivot element as said before. Elements less than 4 to the left side of the screen, and elements greater than 4 to the right side. So here again we have to sort this list taking 1 as the pivot element, 0 at the left side, and 3 and 2 at the right side. So again 3 and 2 got swapped, and here is the swapped elements. So and again to keeping 2 as the pivot element, the element is listed as it is, that is 3. So coming to the right side of the element, 7, 6, 8, 9. So 5 being the pivot value and 7, 6, 8, 9 being at the right side of the list, we have to take the element as it is, and taking 8 as the pivot element, 6 and 7 have been swapped as 6 is less than 8 and 7 is also less than 8, but 9 is greater than 8 to the another side. So 9 and 6 being the pivot value, and again taking the 7 as a pivot value. Now we can observe the table over here. We take the elements of 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So these elements are sorted by quicksort. So here is the conclusion part of this presentation. Quicksort works rapidly and more effectively. It has the best time complexity when compared to the other sorting algorithms. It also reduces the worst case efficiency. Quicksort has a space complexity of O into log n, making it an excellent choice for situations when space is limited. It's important to know its limitation before implementing it, as it's not suitable for small database. Thank you for listening. Please do like the video. Thank you.